Thanks everybody for coming. I'm really thrilled to have here Fan Li, who is a professor at Duke, and I think one of the people that has many accomplishments, including like being an editor of JASA, and has many contributions on the intersection of Bayesian inference and causal inference. And I think is one of the people that can talk to the subject with most authority. And so I'm just super thrilled to have her here today. And thank you, and also thanks to your students that have given you 15 minutes to do this. So we're going to be a little bit tighter than usual. We'll be a little bit more disciplined with questions. Please use the question box, and thanks very much, Fan.
Thanks a lot. Thanks, David, for inviting me to. Thanks for organizing this webinar on Bayesian causal inference. It's very timely, and so I. Again, so just something. I'm actually teaching at 12 o'clock. And my the classroom is a bit work from my office, so I have to. But I thought I postponed it for 15 minutes, but I really have to finish at 12:05. So I will have 2 or 3 breaks for questions, and so we will. I know this is given such a conceptual problem. Topic, we will have a lot of questions, but if you have questions and I didn't have time to answer, to discuss, you're welcome to email me after the talk, and maybe I'll come back to talk about this topic again. So anyway, with this, no further ado, I will start my talk. So again, I changed my title a bit, make it more general. Originally, I was just talking about propensity score, but today is more general about Bayesian causal inference, how and why, and you will see propensity score play a huge role there. And so again, starting just today, we will proceed from the potential outcome framework, the so-called Neyman-Rubin causal model. So we are not going to talk about the Pearl's DAG approach or Bayesian network approach called inference. So the scope is limited to this framework. But there's, as you can see, there's a lot to talk. So basic setup. Let's say now we have a random sample of n units from a target population. So each unit receive a treatment, and this treatment have 2 levels, 0, 1. Okay, and for each person, we observe the treatment status, we observe a vector of covariates or confounders, and an outcome. So then the key point is that under this potential outcome framework, if we assume this thing called pseudo stable unit treatment value assumption, we will each person have 2 potential outcomes, y1 and y0. And the key thing is, under this assumption, under this framework, the causal effect is just a comparison of the potential outcomes on the treatment on the control for the same group, for same set of units. So you're comparing apples and with apples. Again, the first 7 slides are kind of pretty standard causal stuff. So if you are familiar with that, you might take a nap. And so common estimate, particularly this thing called average treatment effect, ATE, or the population average treatment effect, is basically the y1 minus y0, the difference, the contrast between the potential outcome for the same person that average over a population. And then if we have this conditional, the average treatment effect conditional on a particular value of covariate, we call it Kate. So that's when we talk about individual treatment effect or heterogeneous treatment effect, that's a common estimate. But we will talk again, folks. Today we will focus a bit on the ATE, and then later when we have high-dimensional problems, if I have time, I will talk a bit about Kate. So, as everyone probably know, the fundamental problem called inference for this framework is that, well, it's nice. Causal estimates is defined as a contrast of 2 potential outcomes for the same person, but in reality, you at most for each person, for each unit, you observe at most 1 of the 2 potential outcomes. So at least half of the data basically missing, right? So that's why causal inference under this framework is essentially a missing data problem. You're missing structurally 0.5%, at least 50% of your data. So then, of course, if we want to estimate this estimate, average treatment effect, we need additional assumptions, right? Without what, then you cannot do anything. So what are the assumptions? Again, this is all pretty standard. The first is called ignorability, or unconfoundedness. The name ignorable will become very clear in the later slides. So this basically say, well, this mathematically just looks like this. What does this really say is just rule out unmeasured confounders, okay? And so under this ignorability, you will see again from just the pure frequentist perspective, or not any perspective, just probability perspective, you can see that ignorability essentially assumes that the distribution of the conditional distribution of the potential outcome on the z, yz, is identifiable by the distribution of the observed y in the treatment z. So this is quite different. This side is the potential outcome. This side is observed outcome. In the observed outcome in the in one group. So we will see that this is essential. And then this thing, which is this thing, probability of z equal 1, basic probability of treatment given covariates, is called the propensity score. And so this assumption, ignorability assumption, is essential. But it's because this assumption on basically say I don't have unmeasured confounders. Well, because it's assumption about something unmeasured, of course it's non-testable from the observed data, right? So that causes a lot of like question marks and resistance, but we will see a bit later. But anyway, we will proceed under that. So the second assumption is called overlap. Overlap, or called positivity. Overlap assumption is really simple. It basically says that this propensity or everyone's probability being assigned to treatment or control is bounded away from 0. Okay, so this assumption looks very like simple, and it's actually testable because you can actually arguably check everyone's. It's not about unmeasured thing. So it's usually, this assumption is usually characterized by the similarity of the covariate distribution between the groups. We call it degree of overlap, okay? So this assumption, again, I will emphasize is essential, but this is often underappreciated and actually often taken for granted. And a quite prominent recent example, I don't have time to go through, but I will mention that, is this David Bly and Yixin Wang, who's a speaker in this series, their recent work, well, their work on the multiple causes. And I have to say that there's a wide consensus in the statistical causal inference literature that method is flawed in the sense that it's basically try to bypass ignorability by sacrificing overlap, and that doesn't work. But again, I don't have time to talk about that. I just give, like, overlap will play a key role in today's talk. And but again, this, I want to point it out that this is often taken for granted and unappreciated. Okay. So now with these two assumptions, we move to identification. Remember, our goal is to identify ATE, right? So under these two assumptions, actually it's very easy. You can show this two formula. The first is just, ATE equals, so what is it? This guy is just the observed distribution, the expectation of observed Y given in a treatment level given X. So this basically say that, well, you have this kind of the conditional mean of the outcome. So ATE is identifiable by the expectation of mu1 minus mu0, basically the conditional mean of the outcome in the treatment group versus control group under ignorability. Okay. Or the second one is, this one is the inverse probability setup. Or construction, basically say that you can actually, instead of doing this, directly get the conditional distribution of Y given X, you can instead, you don't do anything about that, the distribution, you're just having a propensity, estimate each person's propensity, and then inverse the propensity. Then you calculate basically the weighted difference between the weighted difference in the outcome, inverse weighted by the propensity in the two groups, then you also get the ATE. Again, this is pure mathematical. This has nothing, this is two ways of identification, okay? And so with this two identification formula, what you can do is relatively simple. So it's obvious there are at least two ways you identify ATE. What do you do? The first one is called the regression, or the so-called outcome modeling. What do? Is you just assume a model. You specify an outcome model for the outcome model for the treatment group and for the control group, or maybe jointly. But the key point is you have an outcome model, and then you predict the mu1 and mu0. You predict the mu1 and mu0, and then you just calculate the difference. Okay, the first one. So the second one is IPW. So IPW, again, you just estimate you post a model, observational study. We don't know propensity score. So what you do is you estimate a propensity, you specify a propensity score model, estimate the propensity, and then you calculate the inverse probability weight, and then you calculate weighted difference. Okay, so these two are, very obvious. This is standard, frequentist approach when you are following directly from the identification formula. And Bayesian hasn't come into picture yet. I will get that there. And the last one, and then the third estimator is called double robust estimator. I don't have much time to talk about this, but the key idea is that, well, you can actually combine this two approach, the outcome modeling and the weighting, using this, you can augment one by another. And there's a formula here. And then this thing called double robust, you use both. Okay, and so they have a lot of nice properties. The key thing, again, I don't have time to talk much about this, but the key point of this is all frequentist so far. This is the recipe in frequentist approach to an estimate ATE, right? So the role of propensity in this approach, in this approach, seem to be pretty obvious, right? If you're doing weighting, like you of course need to calculate the propensity and then do the inverse, and you do DR, you definitely need to use that. So in the outcome, but then you can see that in the outcome model approach, propensity doesn't play a role. Okay, so that is actually where this is interesting. In outcome modeling actually is crucial for propensity, for the Bayesian analysis. And I will get to this point very soon. So my point is that the role of propensity is obvious under the weighting and DR approach. How about Bayesian? Okay, so now we get to the core, the Bayesian. What we want to say. So what's the main topic? So Bayesian. So each unit has three. Each unit has three observed quantities: treatment, covariates, and outcome. And so then now, besides the overlap of ignorability, we also assume this unit exchangeability. Again, this is of this triplets. Again, this is more conceptual. I don't see practically it's too big of a deal. But then with all of this assumption, what we can do is we can factorize the joint density function of this random variables as this. So the key thing is you can, so there's four variable. Well, so I actually should say the y1, well, so y1, y0, it's there's a relation between that and the yz. Again, this is a technical thing. You just bear with me. So the key point is that you can decompose, you can factorize the joint density, probability density into three parts. One is the marginal distribution of x. The other one is the conditional the propensity. This is basically the propensity, that the distribution of the density of the treatment probability given x. And the last one is given x and the potential outcome distribution, or the outcome distribution given x. And oh, sorry, this is x and z. Well, anyway, I'll get to the next one. This is, there's some technical. I think I was a little bit misheard, but the key point I was saying that there's three parts components here, and each component has its I denoted the parameters as tau z and tau y and sorry, theta z, theta y, and theta x. Okay, so again, our goal is to still try to estimate the ATE, right? So then let's look at what we can do with what is the identification formula now based on outcome modeling. If we just do the outcome modeling, so we can write it here. Remember, we specify outcome model. And for the y1, for the treatment group and for the control group. And now if we integrate all x, then that is our ATE, right? So now we're getting to the core of the thing. How do we conduct the Bayesian modeling, Bayesian outcome modeling, actually, to get the causal effect? So we need an additional assumption. This additional assumption is the parameters for those three different models, they are a priori distinct and independent. So basically they have independent prior. They need to be distinct, and also they have independent prior. So under this assumption, under this assumption and also the previous assumptions, then the posterior distribution of the causal parameters. Again, what do we mean by causal parameters here is tau, right? But tau, you can see, is really a function of both y and both theta y and theta x. So, but then the likelihood has all three components. But with this assumption, we can see that, well, the posterior distribution of all the parameters theta x, theta z, and theta y is proportional to three part. Okay, it's proportional to this the marginal distribution of x, the propensity. This is basically the propensity, the probability of z given x, and the outcome model, the probability of y, the distribution of y given z and x. And because the priors, they are a priori independent, so the priors can be separated. Okay, so then let's look at this. So you can look at this in this factorization, we can see that this, because of the prior independence. So you can see that this part, because the key thing is ATE as a causal parameter, it involves only theta y and theta x. It doesn't involve any parameter about the propensity score. In other words, a so-called assignment mechanism. So this thing dropped out. So basically, the Bayesian inference of, if you assume the A2 to A4, if you assume this, then Bayesian inference of ATE actually does not depend on the propensity score, right? That's what this thing called propensity score, because this parameter has nothing to do with this, and the prior independence basically went out. So that is why the name that's why actually unconfoundedness assumption has also called ignorable. Basically, under this assumption and additional assumption of the a priori independence, the propensity score is actually drop out, that component drop out from the Bayesian inference of causal effect. So that is pointed out by Rubin in 1978, a long time ago. Okay, so now the interesting thing becomes, this is an obvious paradox here, or contradiction of the role of propensity score in causal inference, right? So first, we just said that, well, in Bayesian inference, if you assume ignorability, then the ATE the inference doesn't depend on the propensity score, so it's ignorable. But on the other hand, one of the most famous paper in causal inference, or maybe in statistics, this Rosenbaum-Rubin 83 paper on propensity score, and the name of that article is The Central Role of Propensity Score in Causal Inference. So that paper say, well, propensity plays a central role, and on the other hand, the Bayesian say, hey, this is ignorable. So what's happening, right? So it's like propensity. So in that paper, that was in the 83 paper, it was purely frequentist. So propensity play a huge role, an obvious central role, and it's very obvious on the frequentist domain. And there's a vast empirical knowledge, evidence that propensity score is important. So then this has become a paradox or contradiction. What is happening? So that's what I try to clarify in today's talk. So one important concept before I get more details is this. Donald Rubin in 2007 had this. He had a paper. He said that basically summarize, advocate this in causal inference. You should separate design and analysis. So again, what is a design? Design basically is a stage that, when you do things without looking at why, and analysis is the part that you do with why. So that is called design and analysis. Okay, so let's look at this. So the Bayesian, so that was actually his idea for a long time, but summarized in 2007. And now let's go back to look at what are the problem we're facing here. So I just mentioned that in the Bayesian outcome modeling thing, again, if we are conditioning on, so if we are conditioned, let's say let's say we're conditional on X, so we don't need to worry about the distribution of X. So then the key point is really this outcome model, the Y given Z and X, right? And so you can see that, well, just by definition, if you are doing a Bayesian, you do a Bayesian outcome model, you specify a Bayesian outcome model for this. So this whole thing involves Y. right? So then, like, and this part is ignorable, so you don't need to worry about it. So then, really, if you just on surface, Bayesian outcome model just by definition only involves this analysis stage. So then the question is, where does the important design stage, which is crucial in causal inference, factor in all of this, right? So to answer that question, I actually made an observation. The observation is about overlap assumption I mentioned earlier. So overlap plays a prominent role in design stage. So again, by overlap, we usually characterize by how the treating group and control group, how similar they are in covariates, right? So usually that plays a huge role in the design stage, which I will clarify in a moment. And we know in the frequentist domain, particularly in the IPW, in the weighting approach, having overlap is very important. The key thing is, if you have lack of overlap, then you will cause this extreme overlap weights, extreme propensity, and then the overlap, then you will have a huge bias and variance. So this is a well-known thing. Okay, so that is, we know that in frequentist domain, lack of overlap is a huge problem. But again, if you just stick on surface, you will say, well, that doesn't seem to factor in Bayesian, because the Bayesian model, the Bayesian outcome approach doesn't have anything to do with propensity, right? So there's some disconnect here. Okay, so then what I want to say is, well, why does overlap matter? And let's view this problem from design perspective. So again, I mentioned, just state again, assume we are conditional on covariance, so we don't need to do the modeling on X. Just a full Bayesian analysis of causal effect only, and assuming the ignorability, only requires specifying outcome model, right? Oopsie, outcome model. So if this model is correctly specified, basically how Y is related to X and Z, if it's correctly specified, the posterior distribution of the theta of theta Y, the parameters, then would be correct. And it's all we need for Bayesian causal inference. We just calculated the posterior distribution of theta Y, then that's enough, because the ITE is a function of theta Y. Again, this is conditional X, which that's a standard way we're doing. Well, life is hard. Like theory is good, life is hard, because we know that in general, outcome models are really correctly specified. If God comes down, tells you the outcome model, then end of the story. But outcome models are really correctly specified. So this is a key. This is the key. You know, when you have in causal inference, when you have two groups, One or two groups, their overlap, their covariance look very different. Or in other words, the lack of overlap, the overlap is very poor. Then you can do a model. Then in the region where the covariates are poorly overlapped, all those causal estimation is purely based on extrapolation. And we know extrapolation is purely, and when you have extrapolation, can be very sensitive and have very large variance. Okay, so the key point is that for causal analysis in the region where the covariates are poorly overlapped, everything, then all the causal estimate is purely based on extrapolation of your outcome model. So then whether your outcome model is correct or not, it's extremely important, or it's extremely sensitive, right? So the one point I want to mention here is that, as you know, as a model base, whether you're Bayesian or you know, likelihood list, when you are doing a modeling outcome model approach, so you write down a model, Y given Z and X itself does not take into account of the degree of overlap. It's just outcome model, right? But it doesn't take care of the overlap, and we know overlap is important. So that is the why I say that we need to take a design, but we need to take a design and analysis perspective. So in the literature, there are two obvious ways. There are two perspectives of improve such, you know, robustness, because we say that when you have lack of overlap, then you're sensitive. So how do we improve that? How do we avoid that kind of problem? So there are two perspectives. From the design perspective, again, design perspective means not looking at Y, just looking at the X and the treatment. So the Rubin 85 already have this idea, say that, well, the key thing is you want to ensure good covariate balance at these, or well, correspondingly, well, consequently also good overlap at the design stage. So at the design stage, prior to do an outcome model. So this is extreme case of this, or the most ideal case of this is randomized experiment. If you have a randomized experiment, their theorem says that actually you can, if you have a randomized study, the treatment group and control group look basically, they are the same, just they should look more or less the same. And this theorem basically say that, you know, in this situation, even you can still do an outcome model on the randomized experiment. Then here, even if your outcome model is misspecified, the ATE estimate is still consistent. Even though, well, if it's misspecified, you will lose some efficiency, but it's still consistent. And this is very well-known result by Ling at 2013. And so, of course, that's like basically, if you have a randomized experiment, in other words, you have an ideal design, whether you have perfect overlap and balance, then you have an out of jail free card, right? You can do outcome model, even if your model is wrong, then you still get consistent estimate of ATE. That's great. Well, but when we do observational study, we don't have that luxury. What do? The idea is then, well, you are actually try to use, you know, try to make your observational data as close as possible to a randomized experiment. How do you do that? Well, you do matching or you do weighting. And usually those methods actually heavily involves the propensity score or the assignment mechanism. Okay, so that's where you can see that propensity score actually enter into the picture. So that's purely from a design perspective. The second is analysis perspective. So the analysis perspective. So analysis perspective is, okay, so there's this model, right? And then you say that this model can be sensitive when in the region of lack of overlaps. How do we deal with that? So then the answer is, well, maybe you should use some very flexible model so that the model, you know, is not too restricted, not just a linear model. You can use flexible models, Bayesian non-parametric models, stuff like that. And hopefully these models actually can also adaptively quantify the uncertainty according to the degree of overlap. So that's a goal, and how to achieve that, that's a different question, right? And another idea is, well, how about just directly incorporating propensity score or the assignment mechanism into the outcome model? So that's another approach. So this is a good time for questions. So I see questions.
So, do you want me to read it out? The one is, what are poorly overlapped covariates?
Oh, well, poorly. So this is a poorly, but basically means that by overlap, I basically means like the balance of the how similar the two groups looks in terms of the treatment group and control group looks in terms of their distribution of covariates. For example, if my treatment group all old people and my control group or young people, so for all old people and my control group or young people, then the age variable here covariate is poorly overlapped or poor balanced. So so what are the thetas? Where do they come from? Oh, so where are the theta? Those are just model parameters. So they are so those thetas, again, that's where, if you oopsie. So the question is, what are those thetas? Well, those thetas are just model parameters for those are essentially the model parameters for the distribution of the treatment, distribution of the covariate, distribution of the outcome. And if you want to be a pure Bayesian or you know, then that's why I assume the unit exchangeability, and then you can use the definity theorem, basically ensure that kind of parameters and with prior exist. So those are.
If I understand you right, the theta x, theta z, and theta y are disjoint as well. They don't share anything.
Yeah. That's assumption. That's actually a very strong assumption. But that's assumption required in this kind of framework, and then later we'll talk about actually the consequence of this assumption. So another question, another question is, in terms of Bayesian approaches, there significant difference between Bayesian non-parametric models regarding the probability. Yeah, I will talk about the, hopefully in the end if I have time. So the key point is the Bayesian non-parametric model. Again, the framework I talked so far is regardless of whether it's it's general. It's regardless whether you're doing Bayesian non-parametric or parametric model. But the Bayesian non-parametric model is give you the flexibility, but it also, but because it uses regularization, it will have some issues, which I will talk in the later part of today's talk if I can get there. So I will talk about that.
Can I, when you talk about model misfit, you can imagine that a situation that's super easy is like, Y, X, and Z all have just 2 states each, and then okay, it's not going to be a thing. But I think that there seems, I think a lot of your interest is maybe when X is very large. So like Y is, did the patient recover? Z is, did you treat them? And X is huge history on that patient or something like this.
Or, we'll talk about that in the high dimensional thing later. Okay. Yeah, so X again. This is even the starting. It's not. I have another question, but I don't have time. I will get that hopefully at the end, and I will come back. Okay.
Okay. Thank you.
Yeah. So now let's just say, as I mentioned, that there then so far has been pretty, overall, like now we're down to the details. So there's another approach, basically say that, well, how about I just directly incorporate the propensity in the outcome model? The result actually is, actually the answer is yes, there are several approaches doing that. And they're very well known. So the first approach is basically using propensity score as an additional covariate in the outcome model. So this was Corey Ziegler has done a bunch of work in this. So the whole point is now you have an outcome model. This model will be actually include both X, Z, and the propensity. Basically, propensity as an additional covariate. Okay, and G is just a function. Okay, so there's several specifications of G. And Ron Little had a bunch of work. So he particularly advocate this. He advocate actually using a parametric portion of X and Z, or X and treatment, and using the propensity and use a penalized spline of the propensity as an additional component. So that is one approach. And a more well-known approach is probably the Hang et al., the pretty well-known Bayesian called the Forest paper. So they're actually talking about, well, separate this, the Y, separate this into 2 models. One is just the distribution, well, one is a function of just covariates and the propensity, and plus then this treatment effect. This part is kind of the treatment effect. Basically, this is actually Kate. So it separates the distribution of X, the contribution of confounders on Y, and the true treatment effect. So that was the idea. But their key point is that, well, then you should actually specify a BART prior for both of these 2 model components, like this tau and F. So, and of course, you can think of this in this approach. You can also think of, well, using this Bayesian non-parametric stuff like that, right? So there are a lot of different approaches. So the point I want to say that this is general. In this framework, like G, you can basically specify a lot of the different type of flexible model like GP or DP and BART, but BART is very common. And again, we will talk about the choice of prior later. The key point is that this approach uses propensity as an additional covariate. And how do you, and in practice, the implementation is actually first, it's 2 stages. First, estimate the propensity score, and then take it separate and take it just as fixed and plug that in to the outcome you specify that and proceed. Okay, so that is the first approach. And some remarks. So the idea here is you can specify some flexible model, non-parametric, Bayesian non-parametric model for G or a parametric model. But if you're already here, why not do something like flexible? So non-parametric prior provides flexibility in modeling. But then why does this E come into play? Well, Ziegler has this point of cut the feedback, but in I would give the intuitive reason for that. It's also adding the propensity score here is almost like an anchor for the robustness. What do I really mean? It's like, So this is a heuristic understanding of this. So this approach is almost like you're almost thinking of, I'm doing an outcome model, but I'm doing outcome model actually conditional on. So in the sense that like at each value or each stratum or each value of the propensity, I do an outcome model. So in a sense, this is almost like a double robust approach. It's like you're basically conducting an outcome regression at the stratum of each value of propensity. So in other words, it's almost like a continuous version of this combining stratification and outcome regression. Again, this is just a heuristic. I'll just give you an idea of why, like what propensity score play a role here. And this type of approach, like using the propensity in the outcome model, has a long tradition in survey. And survey actually has a very close connection to causal inference. I don't have time to talk about that, but the whole point is that in survey literature, for almost 50 years, people have been used the sampling weights in survey. Well, sampling weights essentially in this case is just propensity to augment their so-called design-based estimate. So this is something not new. This has been used before, okay? But then, so this is one of the most popular approach in the current Bayesian causal inference, again, in this domain. But there's some controversial, or I would call conceptual uneasiness. So the first thing is, this is really not fully Bayesian, right? Because we're doing a two-stage thing. We estimate the propensity score first as a fixed, and then we plug in the outcome model. So this is not fully Bayesian. And the second one is really Wasman had this argument, like the key thing is why does, when we talk about outcome model, it's really talking about the potential outcome generating process, right? So why does that has to depend on the assignment mechanism? Well, like why the process I generate the true outcome has anything to do with how I assign my treatments, right? It looks like the assigned treatment seem to be a completely like a separate process, right? So this, again, assignment mechanism is basically the characterized by propensity score. So this mentally seem to be very unnatural. And then like this is one big argument against this type of approach. And I will give some comments later, but I will now move to the second approach. So the second approach is remember earlier we say that all this whole business, the framework we talk about so far, assume this in priori, the independent priors for the model parameters for these three models, for the outcome, for the treatment, for the covariates, right? And why that, like, well, maybe actually that is a strong, because how do I know a priori? They're actually really independent, and they later we'll see in high dimensional case, this kind of thing often actually induce a priori bias. So the idea is, well, maybe let's specify priors of outcome model actually can dependent on propensity score. Okay, so there's some papers actually. Hamlin and 2007 has a very nice paper. It's little known, but it's have a Gaussian process prior for the outcome model that dependent on propensity score, which achieves the similar frequencies approach as the IPW, and then similar. So Chris Sims, also the Nobel laureate, and who also gave talk in this series. He actually has an epic debate against Robinson Wasman on this approach, on this topic. He also constructs some priors, actually also depend on PS essentially, and achieves the frequentist property, and also another work done by Wang et al. In 2012. So this you can view it as a full Bayesian, because it's a full Bayesian, but they use dependent priors. So the limitation of this, the limitation of this is really, it's applicable only to a few special cases. It's very hard actually to design those priors that are actually dependent and have a good frequentist property. So it's only applied to a few special cases. It's not generally not very useful. So it is very nice conceptually, but practically, it just don't see how this can be applied. So the third approach it's very interesting. Also, the second approach is, okay, I'm going to take a posterior predictive perspective. This is purely motivated from the double robust estimation perspective. So the procedure is like this. The procedure is very interesting. So the procedure is, okay, I'm going to separately specify a Bayesian propensity score model. I'm also and a separate Bayesian outcome model. So then, of course, from this both of these models, I can draw the posterior predictive jaws of the propensity and also missing potential outcomes or the potential outcomes, right? So then I have this two set of the propensity and the posterior predictive jaws of the propensity and the potential outcome, and then I can just plug this into the double robust estimator we introduced earlier, and then you get this posterior predictive distribution of the double robust estimate, right? So that is procedure-wise, it's very, very simple and very easy to implement, and also it gives you, so this gives you, so then you can actually specify, you can choose whatever flexible priors or models you want to use for the propensity and outcome. It's just separate, and then you combine the two, use the double robust estimator. And some recent work actually connected to the feature randomization perspective and off the shelf. Now I don't have time to talk about that, but again, I think this is a nice approach, and it's a very flexible choice of models, has a lot of advantages. But the same thing, it has some conceptual controversy because this is not fully Bayesian. Okay, this is really two-stage approach, and then by fully Bayesian, I basically mean that you have a coherent Bayesian model for the outcome, and then you draw the causal estimate. You have a prior, and then draw the posterior from that model of the causal parameter. And this approach is not fully Bayesian. So the last approach, again, you can see that this is already a different approach. So the last approach is we talked earlier. It's purely just use propensity score only in the design stage. So the idea is basically use the propensity to do matching or weighting, whatever, but use propensity in the first design stage to make observational data as close as possible to a randomized experiment. And then once you have this design stage, you have this sample, this match sample, weight sample that is balanced. The treatment group and control group look similar. What you do is then in the design stage, you just apply your favorite Bayesian outcome model to then fit into the balanced sample, and then that's it. So this is a complete separation of Bayes, the design and analysis. So you can see that this is fully Bayesian, right? It's like propensity score play a huge role, but it's plays a separate role from the design stage. So those are the approaches. And I will later, so you might want to know like how I view of these different approaches. And I think each approach has its pros and cons, and how we are choosing that is really case dependent. But before I go to more kind of my comments about comparing those methods or which one is better or whether there's actually no such answer, I want to get to the two kind of important technical issues, but very related, but very relevant to the implementation of any methods I'm talking about here. So particularly is about high dimensional case. So all these methods they're fully Bayesian or not. The key point is that you want to specify a good outcome model, right? If your outcome model is poor, then you cannot get much good result. So now in recent, as David also mentioned, that a lot of challenge of causal inference really come from high dimensional data. When we have high dimensional X, right, and when they have heterogeneous treatment effects, it's not only you have ATE, you also have those Kate. So what should we do there? And then, well, that's a big question. But what I want to emphasize here is like high dimensional data brings some unique challenges unique problem to Bayesian causal inference. So Robbins et al. View that, propensity score, they view propensity score as a crucial dimension reduction tool in high dimensional data. And so they feel that is important. And but what is specific to Bayesian, which is I want to emphasize, is this so-called regularization-induced confounding. So the key point is that for the Bayesian high-dimensional methods, I mean, they are Bayesian non-parametric priors or sparsity-induced priors, spike slack priors, or those things. So the key feature of all of this Bayesian high-dimensional methods is they impose the regularization. They impose regularization through an informative prior on the parameters, right? And so Han et al. Actually in 2018, they realized such regularization come at a cost in terms of causal inference. Is basically the causal inference. When you have high dimensional data, you have a lot of nuisance parameters. You have nuisance parameter, and regularization on those nuisance parameters, they actually in a causal model can induce bias, even though like this is this is like unpurposely, like it just will induce bias. And this problem become this was clarified in a recent paper by Antonio Linaro. This is a very nice paper. So he, in the 2012 last year's paper. So here he showed this thing. So he defined the so-called selection bias. What is a selection bias? It's just the difference between the conditional, the mean of Y in the treatment group, in the group Z, versus the potential outcome distribution, the expectation of the potential outcome on the Z. So again, in randomized experiment, these two are the same, right? But in the in observational study, these two are different. And again, this is unconditional X. So this is unconditional. This is called selection bias. And so he showed this result, and it's very cool. He showed an example that when you just assume you do this kind of both propensity score and the outcome modeling. So if you impose a naive Bayesian shrink prior to the outcome model and to the propensity score model, like for example, in the Bayesian causal forest, that kind of analysis modeling, then he found actually the prior distribution of the selection bias concentrates sharply around 0 as P increase. So the whole point is that, when you are using this kind of naive shrinkage prior, so the bar, this example is actually from a barred prior. So just because once you are assuming, the point is that if you are assuming a priori, the prior independence between the treatment, the outcome model and the propensity score model, then he showed that you use this bar prior just naively, then you can see that as your dimension as the dimension increase, this selection bias will sharply become more and more concentrated around 0. In other words, that using those naive priors, just use a bar prior without doing any other things, then just a priori as your dimension increases, you will, like your prior will increase very sharply around 0. So that means that, even if you have data, then you have less and less chance actually to recover the truth, because the prior, the selection bias will just be, kind of the A4 assumption, the assumption of prior independence, the so-called Bayesian ignorability, will just a priori kind of assume away all selection bias. And this is really, this in Bayesian literature, this is called prior dogmatism. And this is an example of that. And this in the context of causal inference. And so this is the first important caveat about Bayesian causal inference in high dimensional case. So the second one is really the choice of a priors. We mentioned that, well, earlier it would be good when you do an outcome model, you do some flexible models, right? So the flexible models, of course, what Bayesian non-parametric priors obviously is a very good approach to do that, but there are so many different ways. And then BART is very popular in recent years, and it's practically good for performance of our software. But BART actually has some issues. It inherently assumes the same tree structure across covariate space, regardless whether you have enough overlap or not, right? And then you can also use derivative process prior, Gaussian process for a tree, gamma tree, whatever you want, right? Then the question is which one to use, which one to choose. This, again, the choice of this is not the choice of this actually is in the causal setting is closely related to the design stage, to how the treatment group and control group, they are overlapped. Okay, the point is that, you know, in causal inference, if the two groups are very similar, like in randomized experiments, whatever model result will return the same result. The thing really becomes very difficult when your treatment group and control group look quite different, when you don't have enough overlap in the covariate space. And so the key of what prior to choose is really how they fare in the when they have how they fare in terms of the lack of overlap. And I emphasize this again, a desirable prior from my perspective should accurately reflect the uncertainty for various degree of the overlap. So this is a quick example that
about 10 minutes.
Yeah, I know, I'm almost done.
All right.
I'm almost done. So I just say so this, but I think this is a nice one. So this is a tool example done by my colleague Sridhar Doctor. So this is a case that I only have one covariate, make life easy, one covariate. And so the upper one is basically the underlying truth. So the treatment group and control group with different colors. And so those dots are basically the units, their outcome. And again, I only have one covariate. Think of this as age, and the outcome is some like treatment, some health outcome. Right? So this is the data, the data are the dots and the treatment group and control group. And so I fit the linear, so LM is a linear model. And this one is BART, I use a BART. And this one is I use a GP, okay? So you can see that, the lower panel is the effect. So I just fit a model, fit those different models here, well, different models, different priors, right? So you can see this is very interesting. So this prominent feature of this example is that this is an example of like lack of overlap. So you can see that the treatment group and control group only, you know, the age, like if age is the only covariate, you have only a little bit overlap in the middle of the data, like the covariates, right? And in the age, you can see that most of them, they are very different. The treatment group are all with the covariates in one end and the control group in the other end. So you can see, in other words, that they're very poor overlap in the two sides, two tails. So you can see what is happening is very interesting. So you can see GP actually when you estimate. So in other words, we have very little information, real information talking about causal estimate here, because you simply don't have enough data of the two groups, right? Of the two groups. So you can see GP actually. So all three methods did pretty similarly in terms of when there enough overlap in the middle of the covariates. But you can see the GP, as we move towards the region of lack of overlap, GP actually adaptively reflect like the confidence band, the credible band actually increase. And so this reflects a large uncertainty due to the lack of overlap. But you can see that the linear model is doing something. It gives increased band, but it's not too much. But you can see that really worrisome thing is about BART. BART, the confidence band, well, here again, credible band, is essentially the same, regardless of where you are in the covariance. So in other words, in those regions, lack of overlap, BART might be is definitely underestimate the uncertainty. Okay, so uncertainty. So it doesn't definitely reflect how the overlap is the uncertainty due to the lack of overlap. And so I see the questions, but I have 10 minutes. I want to jump. So I will now just quickly wrap up this whole thing. So I kind of give you an overview of the problems and the key issue and the approaches in the Bayesian causal inference, or particularly the role of propensity score. So I want to conclude this by quoting some discussions. I like Dan Rubin's 2014 quote. He said that any complications that create problems for one form of inference create problems for all forms of inference, just in different ways. So the point is that frequentist or Bayesian approach to causal inference, they are both having, they have unique issues, but they fundamentally, the fundamental problem of causal inference, that's really the core issue here. So now we're talking about, people talk about Bayesian, people talk about causal inference, and both become very popular in research. So combine this two topic, anything special? There's anything special. The first thing is, well, the role of propensity score, as we mentioned earlier, seem to be paradox, but as I go through this, I hope that towards the end of the day, seeing that it's not particularly paradoxical if you take a view of separating design and analysis. And also in high dimensional settings, there's some specific issues of the regularization induced confounding. And also lack of overlap. The lack of overlap in Bayesian approach to causal inference will means that the result will be sensitive to the choice of priors and also the outcome model. And the last point, I don't have time to talk about it. I will skip that. So now the question is, when and why to use Bayesian? Again, myself, I'm a pragmatic. I'm not really just Bayesian. So I always, if I choose a mode of inference, usually I feel that it must have a reason. So people often ask, why do I use Bayesian? Of course, you have this usual arguments. You have uncertainty of quantification, not to rely on large sample asymptotics, all that kind of thing. So what is special about causal inference? Why in causal inference we want, or sometimes why or when we should use Bayesian? It's, well, because Bayesian inference allow easy inference of individual causal effects. Once you have outcome model for each person at any covariates value, you can just use the Bayesian crank, and then you can get it. You can get the outcome. You can estimate the treatment effect, and you can combine it with a decision theory. And it's particularly powerful is you have the Bayesian toolbox when you have complex data, like a lot of setting spatial and temporal data or post-treatment confounding, and all of this thing, you can use this advanced Bayesian model, so Bayesian parametric model selection and averaging, those kind of tools, actually use this toolbox to enhance the outcome model in causal inference. So that is very useful. For simple problems, I don't see a point of have to use Bayesian for randomized experiment. So just final words. I want to say that both design and analysis stage are central to causal inference. And a full Bayesian causal model, by definition, only involves the analysis stage. So, and that's not adequate. So then it's a key, I would say that any proper Bayesian causal inference must take into account of the design or assignment mechanism or propensity score. They're kind of essentially the same thing, either in the design or the analysis stage, or ideally in both stages. So I want to say that the ultimate goal in causal inference is to estimate causal effect. It's not to be a Bayesian or frequentist. So the choice of the mode of inference is really case dependent. So that's my final word is, for causal inference, or I would argue for anything statistic, being Bayesian should be a tool, not a goal. And don't be religious Bayesian. That's it. So that's my talk, and I already have 5 minutes, so I have a bunch of, I will look at the questions here. So the first question is, usually propensity score is used to create more probabilistic independence. What in the Bayesian framework? I don't quite understand this question. Propensity score, I know that the use is usually in causal inference is usually try to use that to get observational data as close as randomized experiment, or use matching or weighting, those kind of approach. So, well, maybe that's what I mean by the independence. So in the Bayesian frameworks, as I mentioned that, it doesn't seem to directly play a role, but once you separate, but the key thing is you can separate this to design stage and analysis stage, and make sure that in the design stage, you use the propensity score to make sure that, you can actually those probabilistic independence indeed holds in your analysis stage. That's what I would say. The second one is, are the BART type priors in the line of Han et al. Applicable to any PO approach? Any potential outcome approach, like approaches commonly met in econometrics linear, like in the RDD stuff or similar, or a BART type of priors, therefore applicable everywhere in potential outcome approaches? Well, the answer to this question is not only BART priors. Gaussian process distributed process, anything you want, like the approach I just mentioned, the outcome approach is you can use anything there, but the key problem is that there's a how do you choose those priors, and they have a concept like you should choose those priors. As I mentioned, that when you have a good overlap, the result will be all very similar. It doesn't matter. So the answer is yes, you can use BART in RDD, you can even use in IB and all that kind of thing, but you need to ask yourself that what does BART really bring there? What if use RDD, the strength of RDD is really in the design, right? And RDD usually have very small neighborhoods, small sample size, and why do I put a BART or any Bayesian non-parametric, this complex model there? It doesn't seem to give you much. In principle, you can do any of the things there in any modeling. It's just, again, why do we do that? So that's the case dependent. So see if the so someone I don't see an overlap with the proposals in you mean some papers, so I don't know this question. So another question is, can the findings you presented in any case translated to DAG and graphical approaches? I don't know, but I feel that if you do Bayesian, I mean, they're a completely different approach, right? And also different goal. But I would say that to do any causal inference, if you want to compare two groups, you want to make sure that the two groups look you want to make sure that they have the two groups, they have enough overlap, or the two groups look similar. Otherwise, it's everything is extrapolation. So the last question, how do we use propensity score only in the design stage specifically? Again, it's just, for example, you do matching, use propensity score matching, or you do propensity score weighting so that you come up with a matched sample or weighted sample, and then you apply your Bayesian model to this weighted sample or matched sample. So I have 2 minutes. I really need to run. I know there probably be more questions. And again, if you have, there's some, there again acknowledgement, and this is an incomplete list of the references, and I sent the slides to David. I don't know whether you're gonna post it, but if you're interested in the slides, and I'm fine, you post it, or you can just shoot me an email. I will send it to you.
Yeah, I can post them. Okay, thanks so much. That was fascinating, and I'm sure there are many more questions. I have a couple, but next time maybe. And
yeah, so happy to just shoot me an email, and happy to discuss.
Okay, all right.
Okay.
Thank you
very much.
and have a good day.
Yeah, bye.
Thanks, everyone.